So we are happy to have Supratim Das from Argonne National Laboratory. He'll be talking about non-resonant new physics in HL LHC and EIC era. Yeah, you can start.
Thanks, Roger. Hi, everyone. Thanks for the opportunity to let me talk to you all. I appreciate it. My talk will cover topics on non-resonant new physics in Large Hadron Collider and electron ion colliders. So let's begin with the standard model. It is a very successful description of known particles and interactions, but it is not complete. For example, it cannot explain neutrino masses and oscillations, the matter-antimatter asymmetry, the nature of dark matter and dark energy, or how gravity fits into the picture. To address these issues, one typically extends the standard model either by adding new particles, such as in 2 Higgs doublet models, Z prime models, or leptoquark models, or by enlarging the underlying gate symmetry, as in left-right symmetric models or grand unified theories. This leads to the central question, among all these possible extensions, which one is actually favored by experimental data? Currently, we do not know the detailed properties of new physics. We do not know its mass scale, its quantum numbers, or how strongly it interacts with the standard model field. So we need a framework that allows us to parameterize its effects without committing to a specific UV model. And this idea is not new. A historical example is Fermi's forced fermion vortex. Before the discovery of W or Z boson, Fermi wrote down a contact interaction describing beta decay. The idea is that we parameterize our lack of knowledge of short distance physics by writing down higher mass dimension operators, which are suppressed by some large scale or cutoff scale. These operators capture the effects of heavy particles that we cannot directly produce. In our case, we extend the standard model by adding all possible higher dimension operators built from standard model field. This framework is called standard model effective field theory, or SMEFT in short. This approach is complementary to resonance searches. Instead of trying to produce new particles directly, SMEFT is useful when the new physics scale is too high for current colliders. But its indirect effects can still appear in precision observables. Then the natural question that follows is that how do we actually construct such an EFT Lagrangian? There are two key ingredients. Number one is the symmetries of the low energy theory. In our case, that's the Lorentz symmetry and the gauge symmetries of the standard model. And the second is the degrees of freedom and their transformation rules. Here we keep the standard model fields and impose the known symmetry representations. Once we specify these, we can systematically list all operators allowed by symmetry, order by order, in the cutoff of the EFT. Okay, great. Now the framework is in place. Let's talk about how SMEFT is used in real calculations and what makes it computationally non-trivial. So there are 3 key steps in the EFT workflow. First is the matching. We start from a UV model, integrate out the heavy fields. This tells us which Wilson coefficients are generated and at what perturbative level. The next is the renormalization group evolution. The heavy field mass scale and the energy scale of the collider are usually not the same. So we do the RG running of the SMEFT couplings down to the experimental scale using RGs. This step captures the logarithmic scaling effect and operator mixing and so on. We'll come back to this in this talk. And the final part is fitting to the data. We compute the corrections to the observables and compare with experimental measurements. This give limit on the Wilson coefficients. So basically, this allows us to infer which combination of SMEFT coefficients are preferred and hence which classes of UV models are favored. Okay, so let's start with the matching. What we have here is that in the case of matching, we need to know the Wilson coefficient in terms of UV model parameters. That basically means that we need to write down the UV Lagrangian first, and then have as matching relations the Wilson coefficient and the UV model parameter as a function of it. This is a schematic diagram which basically shows the same idea, that if you have a new physics which is coupling to the standard model, and you integrate it out, so you write down a bunch of contact interactions, and these contact interactions are called effective operators, and their coefficients are called Wilson coefficients, and they are suppressed by the cutoff of the EFT. At mass dimension 6, the cutoff will be 1 by lambda square in the denominator, and at higher mass dimension, at dimension 8, it would be 1 by lambda 4, and so on. That's the EFT example. The low energy theory, which is the standard model, in our case, stays just the same, and that's it. The next part is understanding the part derivative part of the matching. That one can say that I am going to integrate out the heavy fields at tree level. One can also integrate out heavy fields at one loop level, and so on. Something to think about is the basis of the EFT. For example, at dimension 5, we already know about Weinberg's operator of neutrino masses. At dimension 6, one of the most popular operator bases is called Warsaw basis. We'll refer to that in next slides. And then we have more operators at dimension 7, dimension 8, and so on and so forth. The truncation of the EFT is mostly dictated by the sensitivity of the observables. If you have a super precisely measured observable, then you want to look at a higher and higher orders in EFT. Cool. Then, because we are talking about matching, the matching is done in two major ways. So one is the diagrammatic method. This is known in many contexts. It is a well-established method to any loop order. And to get the results in diagrammatic method, one needs the off-shell basis, and then using the one light particle irreducible diagrams, one write down the matching relation in the off-shell basis, and then uses the redundancy relations to get the final on-shell basis matching result. Whereas in the case of functional methods, one uses a predefined formula, which is manifestly gauge invariant formula, which is in manifestly gauge invariant formulation, and it involves computing traces of effective action formula. I have personally worked in functional methods, so I'm going to move ahead with more description of functional methods, but I will come back to diagrammatic method in some time. So the basic idea is this, that you have an action, and the action is dependent upon light field. In our cases, these are the SM fields, and there is a heavy field. This heavy field right now, I'm not defining in terms of any quantum number, but at a later stage, when we talk about model-specific matching, then these heavy fields will be known in terms of their quantum numbers and how they interact with the standard model by the BSM Lagrangian. The point of this particular equation is that we can recognize a classical configuration of the heavy field, which is defined obviously by the Euler-Lagrange equation. And then one can expand around this phi c, which is the classical configuration of the heavy field. And then one can get the tree level matching from the first term. The second term vanishes by the definition of phi c. The third term represents the one loop contribution. So each eta is basically the loop propagator. So you can make one loop diagram using eta square structures. The next step is very standard. What people do is that they sum over all configurations of eta, and what they end up having is a trace of log of second derivative of action. The main point that I would like to note in this whole slide is that the right hand side of this particular equation is dependent only on the couplings of the heavy field and the standard model field and its quantum number. The implication of this statement is that if you can algorithmically implement the right hand side in a computer package, but by just mentioning the quantum number of the heavy field and the interactions it has with the standard model field, one can write down the effective Lagrangian right away without knowing the low energy basis, the EFT basis. Also, this is important in the sense that anyone who has tried analytically computing one loop matching for BSMs, one might have faced problems of two different problems. One is the complexity of the calculation analytically done, and second one is the amount of cross check one has to do to get the results correctly. This has been well documented in 2018, around 2018, 2017 papers. So the automation of the matching procedure was super helpful and useful around that time. And I'm stressing on this particular point because I'll talk about the matching packages in the next slide. Let me start with the 2018 work that was done with my PhD supervisor, Professor Joydeep Chakraborty, and currently in Calcutta University, Professor Sunanda Patra. The point of that particular package was exactly this, that we'll compute up to one loop for any generic given BSM. If we know the BSM Lagrangian, we should be able to write down the Wilson coefficient in symbolic terms of the BSM parameters. This is basically the workflow of the package. One needs to define the heavy field. Basically, this means knowing the quantum numbers under the SM gauge field, SM gauge gauge symmetry. And then based on that, one can write down the Lagrangian, because you're basically writing terms like H dagger H, standard model Higgs dagger Higgs times whatever heavy field you have. And that's all. After that, everything is automatized. You should be able to compute the Wilson coefficient automatically. I need to mention a couple of more packages that have that arrived after Codec, and these are Matchmaker EFT, which utilizes diagrammatic method. The way it computes is that it computes the UV loops. Then it matches with the EFT by using by recognizing the invariance of kinematic variables, for example, dot products of momentum, and then writes down the Wilson coefficients in terms of BSM parameters. And then there is one more package, Machete, which uses the exactly same feature of functional methods. It has a functional formula. It needs to know the quantum numbers of the heavy field and the Lagrangian couplings, and then it computes the effective Lagrangian. Okay, but then the main question becomes, what do these packages buy us, right? Why do we need to learn these packages? How to use them, and what's the value? And this is the slide.
Can I interrupt just like one question? Sure. Can this handle if any fields get a wave? Will it incorporate that or?
Excellent. That's a great question. So when I'm saying that, when we say that we have a symmetry breaking, then the low energy theory becomes not SMEFT but something else, right? So if my EFT basis is defined, let's say the low energy EFT, which has broken standard model in the sense the broken phase standard model, then yes, it is possible to do the matching.
So those packages will automatically, write down the effective theory that follows by including the wave. That
is right. That's expected. Okay. Yes.
But you have to specify which fields get a wave or something?
Yes. One has to write down. For example, I'm thinking right now about Matchmaker EFT. Yes, and then one has to write down, just like fine rules implementation, one has to write down how to expand the field. Yes.
Okay.
I have a question.
Sure.
Yeah. See, when you said you integrated out something, okay,
right,
which means that the result that you get will be sensitive to some regularization parameter or renormalization procedure and things like that, or it is just some number that you get actually without any divergences. And
great. No, that's a great question. Yes. Let me just really quickly go to just to answer your question completely. The matching is
talk about this. It's okay. Yeah.
I think I should answer your question if that's okay right now. Let me just go to the condition, matching condition. This is the matching condition. Basically, if I'm thinking about one loop matching, I will compute for a given process the full one loop in the full theory minus the EFT contribution to the exactly same amplitude, including the counter terms, and whatever remains is the matching condition. So yes, it is dependent upon regularization and renormalization scheme. Here it is shown in MS bar. Yeah.
So you do it
We do it in MS bar.
MS bar.
Right.
Sorry, in the
Thank you.
EFT also you do the loop calculations or what? Or is that handled at tree
Yes.
level?
That is right. EFT also has the loop calculation.
And if you're thinking in terms of momentum, so it has
Right.
unrestricted momentum in the loops, or how do you do this?
Excellent.
Yeah, if
So
you're doing MS bar, there is no notion of this thing. But if you think of it in terms of momentum cutoff or something, in the EFT,
Right.
do you do the momenta unrestricted or what?
Right.
Because
So
there is some ambiguity. How you do this thing in the EFT is not clear.
Right. Right. Excellent. So what I understood is using momentum cutoff. Usually, people in modern EFTs, people use a dimensional regularization.
Okay, then you can
And
give the answer in terms of dimensional regularization. That's fine. So what do you
Right. So
just compute in dimensional regularization and then do this procedure, right?
Yes. Yes.
So there is
that's right.
no
And
notion of restricting momenta, like up to what scale things are included, nothing like that. And it's
nothing like that.
automatically
Right.
taken care of in doing the matching. Is that?
That's right. Yes.
Because strictly speaking, I'm supposed to use the EFT only below some scale.
Yes.
That's the strict definition of what we mean by an EFT. But it becomes a bit of a definition how you handle it when you do loops with EFT. So which is
Right.
what I was trying to get a sense of, is there some subtlety here, anything that has to be specified, or you just naively just do this prescription and it'll work?
No, that's a great question. So when you're thinking about one loop, how do you regularize your loop? That's the question I think you're asking. And then
No, it's
there are
specifically
schemes.
about doing loops with EFTs. Because in the strict sense, EFT is supposed to be a theory valid below some scale. But if you use dimensional regularization, there is no such notion. So
Right.
you have to specify more clearly what it is that you mean when you say it's an EFT. Okay, never mind. We can, yeah.
Yeah, right.
Yeah, I don't want to hold you up on this thing. We can talk about this later.
Yeah.
Right, cool.
The follow-up questions like when you introduce scale in EFT, so you associate some lambda, and when you do the loop computation in the cutoff, so there is also a lambda cutoff. So the same questions whether these two lambdas are same or different.
These two lambdas are completely different, and this is what I'm citing from Anish Manohar's lectures. Here, what he's commenting and what usually is done is that when you're thinking about cutoff in momentum in the loop, this is this is a momentum cutoff scheme, and it has problems in terms of gauge invariance and chiral symmetry invariance. People use for EFT loops, particularly I'm saying, people use dimensional regularization, and in dimensional regularization, the only thing that you get after completing the integration is log of mu square by m square. So there is no spurious scales out of the integral, and then you put ms bar on top of it. Does that answer your question?
Yes.
So is
Okay,
there a
awesome.
clear statement that you can make if you do momentum cutoff? Is there a clear way to state this thing on how you would handle it? Because even there is a confusion. Or is that all straightforward there?
So there, as you mentioned, there are two things. One is the loop computation, and one is the validity of the EFT. The EFT is not valid after above 1 by n square.
I'm always talking about the loop computation. You said you're going to do the loops in EFT, and if I do the momentum cutoff, then it is not clear how I should do this thing, because you're supposed to not be dealing with the EFT above the cutoff scale. But when you do loops, there is no such restriction. It will see arbitrarily large momenta. So there is some problem here, which you have to clearly state how this is rectified, right?
Yes, and the statement here is that when I'm doing the loop, I will do dimensional regularization.
Okay, in dimensional regularization, you don't see this confusion, but
yes, as you
I
said,
believe
yes.
it's a physical problem that you have to still say in some way. But okay, we can postpone this thing. Yeah.
Awesome. Thank you.
But
Okay.
in dimensional regularization, there's no cutoff. Yeah, there should be an analog. So what is it? How do you?
Hi, Supratim, I had a question.
Sure.
So, in your formalism, are you assuming that your UV fields that you have, they're largely classical and the quantum fluctuations are small, so you can just treat it as a background field and then you can do perturbations or loop computations around it? Is it the formalism that you're
Exactly.
discussing, or?
Exactly. These are short scale physics. Yes. Yes.
Okay. And are there examples where you have like a largely classical background? For example, in some cases, if you know that there are these large occupation numbers of the fields, they are largely classical because the momentum modes are occupied and they can be described as a classical physics. So are there
Right.
scenarios in your examples where these become classical due to some reasons at very high energies?
I don't think so. No, most of these are like really heavy physics, and my quantum
It is a
fluctuations are
quantum
small.
field theory, but it can have some momentum
Right.
modes are occupied very strongly. The occupation numbers are so large that they behave as a classical field.
I guess I don't have example for that.
Okay, so you when you develop your formalism, you have any specific examples in mind, or it is just you do a general one?
So I'm considering standard model extensions, like beyond standard model extensions. Now, how does it relate to the examples that you're citing? I do not know. But for me, my heavy physics is always above 1 TeV. Does that answer your
it's
question?
largely classical with small quantum fluctuations. That's what you have, and then you are doing an expansion in the small quantum fluctuations, as far as I understand.
That is right. Yes.
Okay. Yeah.
So what I was trying to point out here is that if you have a package, there are two things. First, it makes the human computation a lot less erroneous, and second, the thing that was almost not possible to compute becomes computable. So this is very useful. This particular slide is trying to point out a couple of important points. The first point is that imagine if you have a single heavy field extension on top of the standard model, and this could be like real singlet scalar. Here, real singlet scalar is represented by this. This is the SU3C, SU2L. I'll come back to the explanation in a moment. But think about a standard model getting extended by one heavy field at a time, and these are the different quantum numbers that you can think about. Then, when you integrate it out, it can result in different scenarios. One could be integration out at tree level. One could be integration out at one loop level, where the internal propagators are only heavy. And also there is another one loop diagram where you can have mixed structure where there could be standard model fields and heavy fields. At the end of the day, all of these are going to give you a contact interaction, although the loop contributions will be 1/16 pi square suppressed. So the point this particular table is trying to say is that for different BSM models, all these Warsaw basis operators that are pointed out in this particular row will get generated at different perturbative levels. However, not all of these operators contribute to the same observable set, right? For example, the first 10 contributes to electroweak precision observables at the leading order, meaning at the tree level. And then these 3 and the remaining here around 15 contributes to electric precision observables at the one loop order, meaning if you invoke these effective operators at one loop diagrams, then it will contribute to electric precision observables. And then there is also Higgs signal strength, where you can see that the QH, QG, these kind of operators enter those observables. So just to get to that particular point, let me just zoom into one particular block here, which is the smallest one. What this particular block is saying is that these are different name of the heavy fields, and this is their quantum numbers. First the color, then isospin, and then hypercharge. And this is the perturbative level this particular operator is generated. So for example, QHD operator, also known as T parameter, is generated at one loop level, and QHWB operator is generated at one loop level. Now one can go down the block and look at the 2HDM, which has almost everything generated at one loop level. So the point that I'm trying to drive here is that if you look at the 2HDM type 1 seesaw or quartet, all these 3 BSM models generate all of these operators at either tree level or one loop level. So that means if you are just looking at electric precision observables, the signature of these 3 would look almost the same, just as arguing from the face value. Similarly, this leptoquark 5.1 and 5.2 will also have similar structures because they have exactly similar perturbative matching relations. However, the 110, the 112, and 130, if you assume that each of these operators contribute differently to the electric precision observables, then they have different signatures. So there are 2 things that we can note here. The first one is that to differentiate between different BSM models, one has to extend the number of observable sets that one want to look at. This is a very trivial statement that you look at more observables, you get better understanding of your new physics. And the second one is the perturbative statement, saying that if you say that I'm just gonna match at tree level, then also it becomes sometimes clear that which one of these Wilson coefficients is generated at tree level and gets the biggest contribution. But this one can also extend this particular statement and say, why stop at tree level? One can also match at dimension 8 level, and it would be much easier to understand how to separate out the signatures of different BSMs from each other. Cool. So just to drive the point home, let me add a graphical interpretation to this. So imagine you're looking at.
Can I ask one?
100%, sure. Go ahead.
Yeah, the previous slide. So these are all scalars or what? These fields that you have?
Good. These are all spin 0. Yeah, they're all heavy spin 0. Yes.
And is this an exhaustive list, or why the particular hypercharge that you have taken? Why not something else?
You mean 110, 112?
Yeah, you seem to be having very specific hypercharges and nothing else. Is it like an exhaustive? Is this all there can be? Or what if I change the hypercharge of something?
No, you can change. You can change the hypercharge. I think it was more interesting to show this. Well, I'm pretty sure that I chose the most interesting ones. S1, which is 111, which is missing here. I think does not have a EWPO structure, and that's why I removed it. So this is not an exhaustive list. Yes.
Okay. Because I could consider something with charge 2/3 perhaps, but you have minus 1/3 somewhere, minus 4/3, but no 2/3.
Right, exactly. There could be more, and then similar kind of statements would be true for them as well.
Okay.
Right. Thanks. Cool. Right. So just trying to drive the point in a graphical manner is that let's say we have some of our most favored BSM models clubbed together, and we do not know how to separate them out. So we consider an observable set, which is in our case EWPO, and EWPO by using the similar arguments could separate them out into 5 classes. then one can use the Higgs signal strength, and then the Higgs signal strength can separate out this BSMs into 6 different classes. One can repeat this particular statement with other observables as well, and then the result would be similar. That you can separate them out. Only the important point is that the separation or segregation by different observables are different. They are not exactly the same. So then, if you do this consecutively, or if you consider the cumulative effect of all observables, then all these single heavy field extensions, except some, could have different structures. Could have unique representation under all these observables. Right? Good. But in terms of fitting, how does it look? Is something like that.
Sorry, I'm a bit lost there. So, how am I supposed to read this this slide, the previous one? Like, what are these S2 delta? They're all fields, right?
Right, exactly.
Which are integrating out.
Yes. So
those are the fields which will, yeah. And what is the next slide? What is the diagram saying? That there is, yeah, then EWPO leading order means what, like tree level, is it?
Right. Yes. So we consider some water services effective operator, and then we look if they are correcting electroweak precision observables at tree level.
Okay, and then what to the right of that first, whatever plane or whatever that, what do I make of that? So I just don't know how to read this slide.
Right. Okay. Let me do this one more time. Thanks for pointing out. So let's say we have around 15 BSM models which we want to study, and as you said, these are just illustrative examples. These are not exhaustive. There could be more. Yeah. And then the next thing, this is just we are using one of the observables. Observable set, and then we are asking that under this observable set, how many signatures can we uniquely derive, just looking from the table. And then
sorry, how many what can we derive?
Unique structures. For example, here when I look at the table, it has this H2 delta 1 and sigma all turned on at the one loop level. So the statement is under electric vision observables leading order, these three will have similar deviations, and we won't be able to differentiate between them. And these three will be clubbed together.
If I look at leading order, then everything that is marked L will not be turned on, is it? Only the T ones will be turned on. Do I have that right?
If I'm looking at, I'm saying L and T both are turned on.
Oh, but then what does leading order? I thought leading order meant tree, no?
Right. There are two things here. One is the matching from the BSM side, and another is the correction of these effective operators going to the observables. So when I'm talking about correction of the observables, I'm saying EWPO leading order. And when I'm talking about matching of a BSM to the EFT, I'm talking about T and L.
Okay.
Sorry if that's confusing.
So leading order means what? In EWPO, leading order means what?
That means that the QHD operator at the tree level corrects the observables that are electric precision observables.
Sorry, can you say that one more time? I lost.
So if I look at the QHD operator also, if I look at the QHD operator and I compute the Feynman rules of QHD operator, that will correct the electric precision observables, which are basically decay with decay with of Z boson to
at tree level.
At tree level, yes, right.
I see. So if I use the QHD and then it is corrected at loop level, then you say that EWPO next to leading order. Is that how you're saying that?
No. But you're right to point out there are two countings here. One is from the matching side and one is from the correction side.
Right. No, I see that distinction. So now I'm talking about EWPO leading order versus EWPO next to leading order. What do they mean?
Right. Then you're asking about this one. So imagine, for example, this QQ1, which is basically a 4 quark operator. So Q bar gamma mu Q, Q bar gamma mu Q. And if you want to think about first generation, that means upward for current. So then what it is saying here is that if you close one of the upward current in a loop, then it can correct Z boson going to 2 fermion. So that's the one loop diagram here we are talking about. That if you enclose this particular effective operator in a one loop diagram, then it corrects an EWPO observable.
Okay.
Awesome.
Sorry. Now back to that full page that flow that you had.
Right.
So how am I supposed to read this now?
Cool. So here what I'm saying is that under a given observable set, this 15 gets segregated into 5 classes, and on top of this segregation, I put on another
means
observable.
what, like five operators for EWPO, is it? What is distinguishing the classes?
Right. The class means a set of BSM models which have exactly similar structure under matching, which these two are, right?
So these classes are the classes of BSM models, you're saying?
Yeah, exactly. Yes. Thanks.
I see.
Right. Good.
Okay.
Just by using EWPO.
And the BSM that gives you those, you're saying I'll not be able to.
It's like we generate the first set of observables in EWPO leading model. You cannot tell these two models apart by doing a matching and testing it with the set of EWPO leading model.
But this I can decide if I give a list of BSM models whether I can distinguish them or not. Or is this? I see.
You match them.
Okay.
And then you try taking one observable after another.
I see.
Try to see how.
Okay, so this is for a given set of BSM theories, then these classes.
So he has chosen these 15 theories here, which are just representative. Supratim, correct me if I'm wrong. And then he has matched them to like various orders, leading or next to leading order, and then he has tested them through the lenses of these 5 sets of observables.
Okay.
And depending on what set of observable, he's trying to see how much you can disentangle these various theories from each other.
Yeah, got it.
Yeah.
So does the order matter here or no?
Supratim can answer that. Yeah.
Thanks, guys. The order should not matter because
Yeah, that's right. Yeah, okay. Thank you. Yeah.
Awesome. Yeah, sure.
Hello. What are the observable comes under the EWPO?
Yeah, these are basically Z bosons decaying into 2 fermions. So it could be 2 up quark, 2 down quark. You can think about mu plus mu, meaning electrons as well. So you're looking at the decay width of Z boson. Cool.
So in the next step, Higgs signal strength. So then again, what are the observable in that level?
Again, the Higgs decay width. You're asking what are the effective operators that correct the Higgs decay width?
I see.
Decay width along with production as well, like
Right.
production times branching ratio, the ratio with the experiment and standard model.
So the first classification after the first layer. So I would expect that it should depend like what are the like model is being considered and what are the process is being considered. Is it true?
Can you please repeat? There was some.
So let's say you have 15 operators, and in the first layer you disentangle them into the 5 groups. But Is it always true, or it depends upon how many operator set you have considered and what are the process you are looked into?
Sorry. Can you please repeat the last question? Something is disturbing the mic.
Are you talking about like some processes which are in this EWPO leading order?
Yeah.
They are not processes. They are basically like some observables. Like this includes Z boson decay width, Z boson, I think also W decay width, and then mass of W and Z, and then several asymmetries. So these are all the electroweak precision observables.
So this classification does not depend what are the processes being considered.
So like you like in this theory, how much like by taking the say like theory number 1, how much does the Z decay width change? And you have your observable. And then you just like pass it through that lens and see like how much it is different from the observable.
He's not giving all the details. I think you should just.
Yeah. Like electroweak precision observables are measurements and with some uncertainties. And with a theory, you get your calculation. And then you just like see how much within error bars these.
So for that, I think it will not be enough because there are so many things here.
Yeah.
If you want to distinguish 15 models, then you better have a lot of data.
Yeah, there's a lot of data. Like each of these layers, each of these contain a lot. Like when he talks about electroweak precision observable leading order, it has say like some 10 observables. Like it's not one observable. Higgs signal strength will have like some 20, 30 observables and so on and so forth. Like every single layer has a lot of observables in them.
Okay.
Juhi has a question here.
Hi. So what are the colors for S and delta? So does it mean that the yellow bars pass all the constraints from EWPO?
The color code, the yellow color code represents that one can uniquely understand their signature. So the S and delta after passing the EWPO yellow is basically saying that I can uniquely identify their deviation from the standard model. Yeah,
so you can distinguish those two models using this set of data. Okay, thanks.
Right.
Sorry, just like the last thing, if I look at the delta and sigma, so after all of these, there is no way to distinguish them. Right. But then is this the entire set of observables possible, or is there some more which I can use to distinguish delta and sigma?
You can use more. This is just.
So this is only after a few of those.
Yes.
Okay. All right. Thank you.
Awesome.
Please continue, Shubhratim.
Thank you. All right. So let's build on top of this. Then the next thing that one wants to look at is an analysis which is a bit more concrete. So imagine having just electroweak precision observables for the moment, and then turning on whatever Wilson coefficients or whatever effective operators contribute to them at the leading order. And then you make a fit saying, which basically means that under the given uncertainties how much space is allowed for my Wilson coefficient. So if you do it in model independent way, you turn on all effective operators at the same time, and you ask the same question, then what you get is a very large space, which is order minus 0.1 to 0.2 in CH, for example. However, when you impose the matching relations with respect to a given BSM model, in our case, these are different laptop works. Their implementation does not concern us for the moment, for the sake of this particular slide. The point that I'm trying to drive here is that if you impose the matching relation, the degree of freedom of fit reduces so much that you can see the allowed parameter space shrinks very near to zero and like orders of magnitude smaller.
Supratim, I have one question. So
Sure.
your model independent, as I understand, is having more parameters, and that is why the constraint is much reduced. And when you do
Exactly.
the forward fitting, I mean, from the just the bottom up approach, you are adding one extension at a time to the standard model,
Right.
like theta 1, theta 2, and omega. So they are only
Right.
populating a particular part in that model independent area. So now the other parts in the model independent area, those actually hints towards any other new physics, or the main interesting part happens in the area that you are seeing populated by theta 1, theta 2, and omega.
So when you say the remaining directions, like let's say there are other Wilson coefficients, they are also functions of the same BSM parameters, right?
No, remaining direction means, let's say I am talking about a particular region where CH is nearly 0.1 and CHG is let's say 0. So around that area is because you are getting it from a model independent reconstruction, let's say something like that. Yeah, okay, using the top down. Now that part is just you are getting because because you are not using any theory, or that is not interesting with respect to the theory. For example, do you get to that part using certain other extension of that of standard model, or that part is not interesting at all using the standard model? My main agenda of asking is to understand that whether model independent approach gives you any extra handle in physics rather than what you are already getting by extending your model beyond standard model.
Right, this is a great point. The answer to your first part of the question, does any other new physics can access that particular point which is discarded by these three? Yes, the answer is yes. In general, you can always find out some BSM model which has, let's say, three BSM at the same time, some weird coupling, and then you can, of course, find out an explanation there. The reasoning behind this is this, that the model independent, by definition, the model independent fit is basically saying that you will find some BSM which will explain this particular point, right? The second particular point is basically answered by my last statement, saying that how does a model independent fit inform me that there is some interesting physics which a model dependent fit does not show? And that's the point, that if you choose any point in the gray, the deeper gray scale, I can find out one BSM model which will explain that data point. Does that answer your question?
Yes, but yeah, it partly. So that means that you are saying that, of course, those will be branches of different branches of new physics, but they can be complicated combination of different beyond standard model. While these, the theta 1, theta 2, and omega, the extension that you are getting, are some straightforward or well-known motivated model
exactly.
extension. Okay, so that means that the reconstruction or the top-down approach is just saying that your beyond standard model extensions are consistent with the model independent approaches, but it does not. The model independent approach does not give you any extra handle apart from the consistency check. Am I right to say that?
I would say so, yes. If you are thinking in terms of simplistic extension, yes, the answer is yes.
Yes, thank you.
Awesome.
If I may add to the point that both of you are saying, that the model independent region, Dhiraj, with more and more accumulation of data, that could shrink in future. Like, because given the present data, it is this. Like in future, like as you are saying that other BSM models can populate different parts of these gray regions, but in future it may happen that like the model independent region itself shrinks to an extent that some of those new physics model cases lie outside that model independent region at that point of time. So the model independent region is something which will keep on changing with the accumulation of more and more data.
I understand. That means that it will, yeah, in future, if it goes to the top right, then you will actually reject this theta 1, theta 2, and omega hypothesis, right? So,
yeah.
Yeah, perfect. Thanks, Anku.
I guess I concluded my matching part. I think you followed up to that point, and the next part that I want to talk about is how heavy physics, the scale of the heavy physics and the scale of collider energy are connected using RG evolution. Please stop me if you have a question. Okay. And then the bigger point is that we want to make our predictions as precise as possible, because then only we can know that the data is agreeing with theoretical prediction or not. Cool. So before talking about renormalization scale, the most exciting thing that I feel about calculation of renormalization is this particular point, saying that when you are considering a UV model, you are matching, let's say, at a given perturbative level, and you end up having a particular operator, whatever. For our discussion, let's assume this is QHD operator, also known as T parameter. And under RG running, you radiatively generate some other operator, which is represented as QH box. Now, it is very much possible that your observable is not sensitive to QHD in the first place, but it is sensitive to QH box. So what it means is that in this way, indirectly, you can put a limit on the mass scale of the new physics just by looking at the RG running of the effective operators. So having said that, let me move ahead with dimension 8 SMEFT renormalization. So the first point that I want to show is that the program that I have started with my host in first postdoc, and this is basically the renormalization of at different cutoffs of SMEFT. So what this table is particularly saying is that if you insert a dimension 5 operator in a loop, what are the things it is going to renormalize? A dimension 5 Weinberg operator is going to renormalize itself. Anything else where there is no take means there is no Feynman diagram. Similarly, if you have two insertion of dimension 5 operators, then you have 1 by lambda from each of those, and then you have 1 by lambda square correction. And in SMEFT, the renormalization works order by order. So if you have a 1 by lambda square renormalization correction, so of course you are going to renormalize dimension 6, which has a 1 by lambda suppression. Similarly, the logic flows to dimension 6, dimension 5 cubes, so on and so forth. The part which would be interesting for this particular talk is how does dimension 8 renormalize different sectors of SMEFT. One thing to point out, wherever there is a green tick, that means it is already known, the anomalous dimensions are already known. The cross signifies that very little or nothing is known, and the gray part is the part we are going to talk about now. I want to point out that this table is slowly evolving, almost like we get to tick out one column once a year, and this is pretty much with my ex-bosses here, Mikhail Chala, Jose Santiago, and my friends in Ghana. Cool. So let's move on with the motivation of doing this particular calculation. So I divide up the motivation into three different categories. One is theoretical, purely theoretical. The second is phenomenological, and the third is computational. So from theory side, one can say that the RGs reveal restrictions on dimension 8 Wilson coefficient space imposed from positivity. What it means is that from positivity, you have theoretical limits on dimension 8 Wilson coefficients, something looking like linear combination of 3 dimension 8 Wilson coefficients greater than equal to 0. So let's say C1 plus C2 plus C3 is greater than equal to 0. Then what do? You impose the RG on top of C1, C2, and C3. Then you end up having a new set of positivity constants on different class. And this is the first point, that by just looking at the RG, you can know under the constraints of positivity which classes of Wilson coefficient cannot have negative value, or their linear combination cannot have a negative value. You can look into more details in this particular paper or the derivation interesting results. And the second point is about phenomenology. So imagine that you have a favorite BSM model, and that particular BSM model does not generate a QHD operator at tree-level integration out. But when you do the RG, you radiatively generate a custodial symmetry violating operator. So this is basically a point parallel to what I mentioned in 2 slides back. that if you start with a BSM model that matches to an operator that does not generate a sensitive Wilson coefficient and operator, but under RG running, you run into something which is super precisely measured, which in this particular case is rho parameter. So you can find discussions of custodial quadruples in these two papers. And the point is very simple, that by looking at the RG running, you can put indirect bounds on the limits on couplings or on the masses of the BSM. And the third point, which I think is super important, is that dimension 8 RG is computed using multiple computational tools are in agreement with each other, and this sort of validates each other. The point is that when you're computing dimension 8 RG, you're using almost the state-of-the-art packages, meaning these packages were not actually written to handle dimension 8, so you're pushing their limits. So this helps in two ways. First is that it prepares them for new calculations, and second is that it validates them. And I'll come back to this particular point when we talk about more details of the computation. Okay. The next thing that we need to talk about is how we set up the computation. So first thing that we need to know is how do we do the expansion that we have already talked about. We have dimension 5 pieces, dimension 6 pieces, and so forth. And if you're looking at correction from a dimension 8 term, then the lowest order correction that you can get is again 1 by lambda for suppressed term, which is itself, or it can get corrected from a dimension 5 and a dimension 7 insertion, because dimension 5 comes with a 1 by lambda, dimension 7 comes with 1 by lambda cube. So if you have a insertion, for example, this is a schematic diagram of the exactly same point, that if you have an insertion of a dimension 5 which is suppressed by 1 by lambda, if you have an insertion of dimension 7 which is suppressed by 1 by lambda cube, then in total you are getting a 1 by lambda 4 suppression, and this will renormalize the dimension 8 operator. And this is the reference that does that particular calculation. Okay, so coming back to the main focus, which is basically this particular term. To calculate this, the first thing that we will need is a basis. And for us, this Green's basis is written in this particular paper by Tala, Carmona, and Geddes. This basis is basically a Green's basis, meaning that your EFT has all those operators on which you have not applied their on-cell relations. So these are more number of operators in comparison to what EFT basis in the on-cell limit. In the case of on-cell EFT dimension 8 basis, this is the well-known paper of Christopher Murphy, where you have almost all operators written out. There are different classes of operators that you can look at dimension 8. If you are thinking about purely bosonic ones, there are 8 insertion of Higgses and so on and so forth, 4 insertion of field strength. But to get a handle on the calculation or to make it practical and minimal, we make the assumption that we are only going to consider those subclasses which are tree level generated when we integrate out a UV model. What does it mean? It means that imagine whatever BSM model you want to imagine, and then you integrate out the heavy fix at the tree level. The statement is that the classes that are shown in the box, they are only generated. So then the point becomes that you are only going to put these guys in the loop to renormalize some other Wilson coefficient. So these things enter here and they renormalize something else. That's pretty much the problem statement. Then the next thing that we need to know is that how do we do the computation? And this is the point about the computation, that we are using a tool chain. First, we need to implement our operators in fine rules. Then we need to create our topologies using fine arts. And then we compute our loops using formcap. This is particularly important because analytically, you can make minor cross checks and partial cross checks, but the whole calculation has to be automatized. It is sort of impossible to do by hand. The next thing that you'll need is how
can I interrupt a little bit?
Sure.
So I'm lost actually. What exactly you are doing actually? Can you just give a flavor of what you are doing with dimension 8 operators? Just give me, I don't understand these details, just the idea behind it actually.
Okay, sure. So the statement is this, that we want to understand how the.
Yeah.
Sorry, go ahead, please.
No,
Okay.
carry on.
So we want to understand how these dimensionate operators are running under RG scale. So the thing that we need to compute are the divergences generated by dimension 8 operator to dimension 8, right? So to set this particular calculation, the first thing that we wrote down here is the basics. Like what are the operators, what dimension 8 operators are there in the on-cell basis, and what dimension 8 operators are there in the off-cell basis. The reasoning goes like this, that we will put the on-cell basis dimension 8 operators in a loop, and then whatever divergence 1 by epsilon pieces that I get will be absorbed in the off-cell basis, and then from there I will get the RC run.
Can I interrupt actually? Just to make it simple.
Yeah.
You have bunch of dimension 8 operators, and you want to study how they evolve under some renormalization group equation.
Right.
Okay. And that requires, if I understand, you need to calculate certain anomalous dimensions. Is that what you are doing?
Yes, that is what I'm doing.
So you compute anomalous dimension, that it's a matrix actually, because you have so many operators, and they mix under renormalization. So you compute for an anomalous dimension matrix for a bunch of dimension 8 operators, and that's what you're doing, or?
Exactly. No, that's exactly. Thanks for pointing out.
What is the dimension of the matrix actually?
That's
how many operators are there?
It's order 100 in the bosonic case, and order.
And you compute everything at one loop level.
One loop level. That is right. Yes.
One loop level. Okay. Thank you. Yeah.
Awesome. Thanks for asking. Right now I'm going to point out.
Sorry to interrupt. Just one thing. So you mentioned about this on-shell basis. But if I use on-shell, am I allowed to use that in the loop or what?
Yes, your loop insertions are on-shell operators, but when you are absorbing the divergences, they are off-shell operators. Then you put a redundant equation on top of off-shell operator to get the on-shell relations.
What does on-shell mean?
The equation of motion applied operators. The equation of motion of Higgs and other formulas.
Okay.
Yeah.
Okay, and it is a complete choice that I have, is it? Whether I use the on-shell or the off-shell? Or off-shell is more general, right?
Yes, off-shell is more general.
So when am I allowed to use the on-shell and when I should not?
Right. So here we are talking about putting the on-shell operators in a loop and understanding how it runs into a different.
No, I'm asking what is the restriction? Diagram. So when am I not supposed to use the on-shell, or can I always use the on-shell?
You can always use the on-shell. Only the caveat is that while absorbing the divergences, it would be very non-trivial to use a on-shell basis. Mathematically, it's desirable to use an off-shell basis to absorb the divergences. Otherwise, always use on-shell. That's the statement.
Yeah.
And there will be infrared divergences and things like that. So usually when people try to compute anomalous dimensions of some local operators, you make sure that there are no infrared divergences by taking external X off-shell, which can make which can only allow you to extract UV divergence, because its anomalous dimensions correspond to UV. So you somehow, by making operators off-shell, you can actually probe the UV part without any contamination from IR.
So it is, if it is a final and initial state legs, then I can see. But if I use an on-shell action, but then use it in the intermediate state, I'm not supposed to do that, right?
Yeah, I think it should not do it. Because
is that a restriction? But he didn't mention it. So am I allowed to use this in intermediate states also, or am I supposed to not use that if I'm using the on-shell?
May I ask what is your intermediate step? Sorry, I didn't get it.
So if I'm using the on-shell, basis, if I have put some fields on-shell, right? Am I allowed to use those fields in intermediate states in loops and so on? Am I allowed to do that?
Your loop insertions are all on-cell operators, yes. But you're absorbing your divergences in off-cell basis.
How is it
you're allowed to do that?
How am I allowed to use an on-shell field as an intermediate state? Doesn't make sense to me, but
let me show you one particular diagram. So let's talk about this schematic diagram. This should be enough. So phi by 1 by lambda 4. Here what you have is h dagger h to the power 4. It's an clearly an on-shell operator. You're closing two of these Higgses in the loop, and then pulling out the standard model quartic coupling. So it is again Higgs, right? So it is self-correcting. Pi 8 is self-correcting itself. From this particular one loop diagram, whatever divergence that comes is absorbed by phi 8 itself, right? So can you ask your question in this context, please?
I guess you're trying to say if I'm after divergences, then even if I use an on-shell field for intermediate state, I'll still be okay. Is that what you're claiming, or? But I have a very simple thing. If I put it on-shell, how am I supposed to use that Higgs field as an intermediate state?
So when you say intermediate state, what does it mean?
Like your loop states, right? You have two Higgs fields in the loop. Am I allowed to do that if I put it on-shell?
Oh, no. They are loop propagators. Why do I?
So then I should not be using the on-shell basis for computing this one, it looks like.
So when I say on-shell basis, that's the basis of the EFTs. And your effective operators are written.
Yeah, but the first blob, which has Higgses, which you say you put on shell, right? There are 8 Higgs fields which you put on shell. But you're using the same Higgs in a loop now.
Okay, I understand the confusion. Thanks for pointing out. The point when I say something on shell, it's the name of the basis. It's not about the loop propagator. I needed to clarify that. So when I'm talking about on-shell basis, that means the basis does not have a double derivative acting on a Higgs. So if you have d squared h in your in any of the operator of your basis, that has to be translated away using equation of motion of Higgs, and it has to be absorbed in some other operator. That's a redundant operator. So when I say on-shell basis, that's the structure of the EFT basis. It does not say anything about the loop propagator on-shell limit.
I see. Okay.
All right. Thanks. Yeah.
So Pratim, you already finished 1 hour 15 minutes. Maybe you can take 10 more minutes. Is that okay?
Sure. I'll just pass the results and summarize if that's cool with you.
Yeah.
Thanks for the reminder. Let me really quickly see. Right. So I'll make quick 2 points. The thing is that there are a lot of cross checks going on because these are super lengthy and complicated calculations, and also people use it for their global fits. So these are something here that I would rather skip because I want to talk a bit about EIC and stuff. Okay, let me really point you to the result. In this particular result, there are 3 take-home messages. First is the thing that the large here in this table, and thanks for pointing out someone and the audience. I cannot really see, but this is the table or the matrix that we want to look at. What this particular table is saying that if you insert an operator from 544 class, which is basically one of the operator of 3 operators this class has, it is going to renormalize operators from the class B2 phi to D2, and it is going to be proportional to G1 squared, right? This is what this particular matrix means. The guys in the blue have a big numerical coefficient sitting in front of it. That's why they are colored in blue. But what's the point? The point is that if you look at the renormalization group flow for one of these Wilson coefficients, it has a contribution which is proportional to itself, but with a huge number, 192 lambda. So the point is that without computing the RGs, we do not know how large is this contribution from the RG. Because people naively say, okay, this is going to be one loop suppressed, 1 by 16 pi square suppressed, but this is not always true. You might have significant contribution from permutation combination of these 8 Higgs layers, right? There is one more comment that one naively can ignore, can pass on, but it's important to make a calculation and check, and that is this: that if you look at topologies that might not be directly connected, for example, psi2 pi 3 d2, then using the redundancy relations, you can find out that some other classes which are not directly topology connected might get RG contribution. Right. I can come back to this matrices if you have a question, but I would like to move on to my next point, which is one quick slide about the complementarity of High-Luminosity LHC and EIC DIS observables. The point here, what I am trying to make in this particular slide is that in the Drellian, what we have is that a work anti-work coming in, and then L plus L minus getting generated, and L is basically L is representing either electron or muon. So in LHC, what we have is we have limited ability to separate flavors, up and down quarks and chiral structures. And at high mass limit, when we want to study four-harmonic operators, we always look at high mass limit because that's where it is more contributing. There, what we suffer from is low statistics, and systematics are controlled by pattern distribution functions. This is where the EIC observables come in. It plays a complementary role, because there what we have is a quark electron scattering, and in EIC the electron is going to be polarized, right? What handle does it give us? It means that we can look at parity violating deep inelastic scattering, meaning that we can look at the scattering of electron which is left-handed, we can look at the scattering of the electron which is right-handed, and then we can subtract and use the asymmetry to find out different limits on different Wilson coefficients, which was totally which Drellian couldn't give us. And the second point is that from EIC, we can look at kaon and charm tagging as well, which is not very good in LHC. And that also leaves some blind directions. So the point of this particular slide is that I am interested in combining these two observable sets together, even though one is going to be order 1 TeV, the other is going to be order 100 TeV, and then we'll need RG, which is very good. But I think combining these two fits together will leave degeneracy. There are some studies already in the literature, and there are much more work that needs to be done. And there is one more thing that I want to mention before closing, and this is about the AI/ML studies that are currently being done. Usually in global fits, we calculate corrections to our observables. Sometimes these corrections are sometimes these corrections have quadratic structures, meaning 2 insertions of dimension 6, for example. And traditional fits can run into local minimum, right, which is not the true minimum. So AI/ML is a complementary avenue which can help us overcome this kind of issue. So what can happen is the new physics may appear as correlated. Subtle distortions over many observables simultaneously because it is not resonant. And then what happens is the traditional operator by operator scans may be diffused or correlated signature, right? So this is where the AI/ML part is very useful because it represents collider observables, for example, differential distribution, as structured data set, which is basically tensors, and the MyML network then learns latent representation that return physically meaningful relationship. The last sentence means that if I have a d-dimensional data, And my ML network reduces or condenses that d-dimensional data sets into something smaller than d-dimensional data. That is called latent representation. And the ML network learns some physics output while doing that condensation. The problem that this process solves is that these patterns are extremely difficult to detect. The pattern in the sense of differential distributions, for example. And if you try to detect using standard one variable analysis or linearized SMEFT templates, for example, we just gave examples why 1 by lambda 4 effects are important. And then if you have the signal is thinly spread around multiple beams, then this is going to be a problem in general for traditional fits. And that's why AI ML solves the problem. But at the end of the day, the final goal is going to be that we provide a differential distribution to an AI ML network, and then it should be able to predict how much Wilson coefficient space is allowed under that given data. Okay. If you want, I can say a bit about my projects that I am interested to work on, but if time allows.
Yeah,
Any
you
comment,
can.
please?
Yeah, you can. Please.
Awesome.
Please.
So currently I'm trying to finish up projects on like right now I'm trying to finish up projects on a dimension 8 SMEFT operator dictionary, which basically means take exhaustive list of single field extensions of the standard model and integrate them all out up to dimension 8 SMEFT, and also compute the Fermionic RG mix. For example, the table that I showed for renormalization status of SMEFT, there are certain cross marks there. Those will be ticked out pretty soon, hopefully. And then there is also the EIC comment that I made, that it is possible to lift flat directions from global fit by combining these two datasets. This is I'm certainly interested in. And then just now I mentioned about AI ML, that ML frameworks can complement the traditional fit. This is something I started after joining Argonne last year. Cool. In the broader sense, my 4 objectives are these: that complete all NLO and dimension 8 consistent analysis for high energy Drelian, diboson, and PBS cells, because people have seen that all these observables are sensitive to 1 by lambda 4, and it is important. In the case of EIC, I'm interested in looking at parity violating charge current and semi-inclusive deep inelastic scattering prediction. Quickly, if I want to say that there are missing gaps there, for example, if you are doing a joint fit, and if the PDFs do not incorporate the SMEFT correction, but SMEFT corrections are only incorporated in observables, these are biased fits and one has to correct that. But this will take some time because one has to first calculate the observables and so on. So this is missing in the EIC phase, and I think I want to compute that. In the AI ML, this has to be made foundational, meaning that one needs to go beyond Drelian and also try to look at different processes that might be useful. And of course, very important that I want to grow my leadership skills and lead or co-lead programs, integrating effective field theory, QCD, machine learning communities for collider physics, and also mentor junior researchers and establish group expertise. So that's all. Thank you so much for your questions and your attention.
Thank you. You have any questions?
I have a question regarding your parity violation at EIC.
Right.
Do you so what is the proportion of gamma to Z that you will expect to see at EIC? I mean, will you see significant amount of Z exchange data?
That's a great question. If I am considering Q square order 100 GeV, then the answer is yes. But the luminosity, yes, the answer is yes. I do not have the numbers right now in top of my head, but that's a great question. But the answer should be yes.
Okay, I see. I just have one comment, not a question. When you say,
Sure.
your first slide that standard model is incomplete because it doesn't have gravity. I mean, standard model was never written down to include gravity. I think it's incomplete more because the Higgs boson mass is not stabilized and other such things, right? Not really because it doesn't include gravity. Just a remark. Yeah? Thanks a lot. Thanks.
I'll refine it. Thanks for pointing that out.
I have a question. Can you go back to just few slides before when you mentioned about dimension 8 operators? You had written one. Yeah, that's where actually you click that just before that, few slides before.
Sure.
No, just next one actually.
Oh, next one. Okay.
No.
Okay.
There's a differential equation for C8, I think.
Right. This one, I think.
This is not this one actually. There's a previously.
Okay. Is that the diagram or the?
No. It is just yes. Just go up actually. Yeah, that one actually click. Is it C? Yeah.
Okay.
So there are some coefficients that I could see. Gamma with many indices. These gammas are just gammas that appear in the previous expression, or with just some combinations of them.
Right. The gammas are anomalous dimensions. These are the things
they are anomalous dimensions that appear in the RG of that operators. No.
Yes.
The same operator.
Yes.
How do you get this expression actually?
Yes, this particular expression is basically saying that at 1 by lambda 4, what are the insertions in the loop that is going to renormalize the dimension 8 operators? So basically, this is the BFT power counting. The first term is saying that it is by itself 1 by lambda 4. The second term here, let me just enlarge it. The second term here is basically saying this is 1 by lambda cube, this is 1 by lambda. And then the third term is each carrying 1 by lambda. So in total, everything is 1 by lambda 4, and that's why it is collecting as C8.
I see.
Usually,
you demand RG equation by demanding some invariance. No, what is that you demand actually here? It's how does this come about actually? I understand there are many insertions that you have to do to get 1 by lambda power 8.
Right. One is the EFT power counting, as I said. The invariance. Let me see. I'm not sure.
Some invariance you have to demand. No, something is in. Yeah, some it's invariant under change of scale or whatever. Some physical.
Right. The Karan-Simons equation. Yes, one has to impose that the scale invariance of the Bayer parameters are equal to 0. And then the Bayer parameters are broken into the renormalized parameters, and then from there I get the anomalous dimension.
Okay.
Is that the right? Yeah.
Okay. Thank you.
Awesome. Thank you for your question.
Sorry, quick question. That 192 that you had. So why is that so big? Do you know why? What happened? Why that was so big?
Yes, this particular case is because of the 8 Higgs legs. There are case-to-case ways one has to look into it. This particular is because of the combinatorics. This is like
combinatorics in what? In the loop, is it?
It's in the loop in a way. This
Sorry,
particular
which one? That is for okay, some loop like that or what?
Exactly. This particular loop has the 192. So the number of ways one can put 2 Higgses together gives us that large number.
Yes. So the number of ways, because you have like 8 Higgses.
Yes.
Number of ways you can contract that will give you some combinatorics. That's the reason for the 192.
Yes. Yes.
Okay. All right. Thank you.
Thank you.
Hello. So I have a very generic question. So how one handles divergences while this dealing with higher dimensional operators in EFT? So can you comment on that?
Sure. So the renormalization works order by order in cutoff your VFT, meaning that if you are renormalizing at a given order, let's say 1 by lambda 4, because that's the equation I have right now in front of me. So this guy is the dimension 8 operator. It comes with 1 by lambda 4, as you can see from this particular term. Let me make it big, sorry. this particular guy comes with 1 by lambda 4, right? So then the next question one should ask is that what other insertions from lower dimensions can give me the 1 by lambda 4 suppression? And that's the answer to your question, that 4 insertions of Weinberg operator, or 2 insertion of Weinberg operator dimension 5 and 1 of dimension 7. So this is the way cutoff, by counting the power of the cutoff, one can renormalize EFTs, SMEFT in particular.
Okay, thank you. Thank you.
Thank you. Yeah.
So these operators, do they contain something gamma related to gamma 5? Like, I just want to know.
Yes, sure. Yes. Yeah, they are chirally defined. And this part, in the bosonic case, no, but in fermions, there will be chiral. They are defined in terms of chiral fermions.
You
yes.
handle that in dimensional regularization again.
The question, I think, that's a great question. One has to be careful about these kind of things. Yes, the generic sentence is that the one has to be careful. Yeah.
Okay, I have one more question. So can you go to this EIC diagram where you have QQ bar going to E plus E minus, and yeah, this one.
Right.
So this, you'll take all the operators which have this thing as a like final state or the
external
initial.
leg.
So you can have gluon also in the initial state, right? Like, because you are taking in Rayleigh, you will be having proton going to L plus L minus, and in EIC you will be having electron proton. So from proton we can have gluon also, as well as quark and antiquark. So we have to include all such operators, right? Or
yes. So here okay. That's a great comment, first of all, and one has to be careful about this kind of analysis, that one needs to take into account all those parties. Yes, answer to the first question is yes. Here, what I wanted to show you is that the complementarity between EIC and High-Luminosity LHC, that they have a common set of operators that they put bound on, and these are semi-electronic 4-harmonic interaction. So that's why I put representative diagrams of these two.
They are sample diagrams.
Yes.
I have one more small doubt. So let's say we have this EIC, this Q, all the processes all the patrons which can come from proton will interact with the electron via Z boson or W plus W minus, because you are considering parity violating terms. So I want to ask, like, if one do explicit computation from, like, we know there are Z boson, we have Lagrangian for Z boson and W plus W minus, and we have a similar Lagrangian for effective theory. If we get some numbers, can we relate those? Or actually, I want to know the relation, because we have the full theory.
Is it audible to him?
Yeah, I was just trying to listen. And yes, that's a great question. But the point is that your EFT here is built on top of the standard model. So I think if I understood correctly, are you saying that you want to integrate out Z and W plus W minus, or you want to understand the correction from SMEFT?
Actually, I want to say like from the SMEFT, maybe. Yes. Sorry.
So the Z is mediating, let's say, 2 fermion to 2 fermion scattering, and in the SMEFT you are saying that there is some new physics that we do not know about, but I have at dimension 6 level there is 4 harmonic operator. So then the next statement becomes that whatever data we have will put some limit on the 4 harmonic operator, and that's the limit we get on the Wilson coefficients. I'm trying to connect from here what you are asking. Can you please help me? I'm not understanding your question.
No, actually, I think I understand. Oh, okay.
Before you end, Supratim, I have this question. Like, when you are discussing the LHC versus EIC complementarity, because the scales are completely different, like, are you thinking of, like, for EIC, like using an LEFT kind of basis, or are you using the SMEFT basis and just going to use the RGEs to, like, deal with both these experiments, or do you have like two bases in mind for such a study?
Great question. Yeah, that's a great question. Because we are thinking about hard. When I'm thinking about the effective term, the four-permanent term, I'm thinking about energy scale above standard model symmetry breaking. So I'm gonna consider SMEFT Wilson coefficients as a interaction for EIC as well. But if we want to consider energy processes when the symmetry is the broken standard model becomes the theory, then one needs to think about left. So okay, summarizing the general answer. So one sentence answer to your question is I'm only thinking in terms of SMEFT.
Yeah.
But,
okay.
Yeah. But one also can think more.
Yeah.
Yeah. Anybody in the online?
Hi, Supratim. I just wanted to ask one question. So
Sure. Thank you.
So, so you have different classes of BSM theories, and you have also an SMEFT. And if I have a UV theory, I can do a Wilsonian RG. I get lots of terms. Now you set a scale to match all of these terms, which is known from SMEFT. Is it what you're trying to do at some high scale, and then after you know the coefficients, you run it down to a lower scale?
Yes, exactly. That's what I'm doing. Yes.
Okay, and then the question is, suppose you have done a Wilsonian RG, you get lots of terms from your UV theory, and what is the possibility that you may lose some of it which are not already there within your SMEFT? They may be there, but they are suppressed at this high scale. Are there possibilities like this?
Yes, that's a great point. If your let's say effective operator is generated at one loop level, right, perturbatively suppressed, then of course I am gonna miss out those kind of suppressed contributions. First point. The second point is that also from the observable point of view, one needs to think like if my observables are precisely measured, then I'm gonna do a higher order perturbative calculation. If it is not sensitive, then probably I'm gonna ignore it.
Okay. Now I'm asking this because you are mentioning EIC. So EIC means how precise data do you need so that you can constrain well your UV theories. For LHC, I can understand there are the high luminosity LHC runs that will happen. So you can constrain your effective theories, SMEFTs very strongly, and then these mismatches may be minimized. But about EIC, how much do you need to know precisely all these processes so that you can do this program very efficiently?
That's a great question. Although I cannot recall the luminosity numbers, but under the current planning that I have seen, that will start in 2035 and onwards, within a good amount of time, the projections say that the EIC bounds will be competitive with high luminosity LHC. I think.
And in EIC also there are these uncertainties comes from PDFs. So in all these processes, so how precise now you have to make the PDF so that you can make meaningful predictions?
That's a great question. I would say it depends on case to case basis. I'm not exactly sure. I would say I have to look into things. I'm not exactly sure.
Thanks, Supratim. Yeah, maybe we'll
Thanks,
end now.
everyone.
Thank you. Thanks a lot.
Cheers.